Hello and welcome. Today we're going to talk about applications of residues to improper real integrals. Okay, so now we're finally getting into what residues are going to do for us in terms of mathematics of a real variable. Okay, so let's recall what an improper integral is. So an improper integral is of the form, we can write it like this: integral from 0 to infinity of f of x dx. All right. So this is actually defined. We don't know much about this thing until we give it a better definition in terms of a limit. It's the limit as some capital R goes to infinity of a regular definite integral that's over a finite interval, right? So what we say is if this limit exists, then what we say is this integral converges. Okay, so for this to converge, this limit has to exist. And then there's also what we call, a different type of integral, different type of improper integral, and that is the double-sided. So this is called a double-sided. Okay, a double-sided improper integral of a real variable. And what we have to do is actually do basically a double limit. Limit of r going to positive infinity of f of x starting from 0 and going to r of f of x dx. Right, I'm going to actually call that r1, okay, plus, and then we have to do another limit for the other side. Limit r2 goes to infinity of negative r2 to 0 f of x dx. And note that, okay, what we have here are two distinct limits that both have to exist independently. We could not write it down with the same letter. R1 and R2 couldn't be the same, a single limit, because it turns out there's some problems there. So, so what we're going to define is, it's not necessarily true then that, so it may be the same though that, so I should say that now we're going to define this other thing called a Cauchy principal value, what was called a Cauchy principal value. A Cauchy principal value, which we actually call, we put this symbol PV, and then we put the integral as follows, okay? And this needs to be kind of thought of as, in quotes, that whole thing, and that's equal to the limit as r goes to infinity, a single r, from negative r to r, f of x dx. And I should say if this limit exists, it's not necessarily true that the integral f of x over the reals converges. And so we can give some examples of that. And what happens is, because if f of x is an odd function, say, whatever advance I make in the r direction, we make some subtraction in the negative r direction, which cancels perfectly. In which case, even though so this limit wouldn't exist, or this limit would exist, but the principal value would definitely exist. but it wouldn't equal the double-sided integral, which would actually not exist at all. It wouldn't even be defined. So let me give you an example of that really quick. So we take f of x to be equal to x, which is definitely an odd function. Okay, so obviously the principal value integral of x dx is going to be equal to the limit as r goes to infinity, negative r to r of x dx, which is equal to limit r goes to infinity of x squared over 2, evaluated at negative r and r, which of course is 0, because for every r value, the difference of these two things when we evaluate it is just going to be, well, it's going to be r squared minus r squared over 2, which is 0, always for every r. So taking r to infinity, it's always equal to 0. All right, so so the Cauchy principal value exists, but clearly limit r1 goes to infinity of 0 to r x dx does not exist. Shouldn't even put an equal sign there. It just, this doesn't exist. And therefore, this integral, this improper integral, does not exist as well. However, if we know that f of x, some function f of x, not necessarily this one, but now on to a different statement, if this converges, then certainly the principal value will as well. Will exist. So we have to be watch out for these things. But one sort of corollary is that if f of x is an even function, then if I write down the principal value as the limit r goes to infinity of negative r to r f of x dx, I can rewrite that as the limit as r goes to infinity of 0 to r f of x dx times 2. In which case, this and its cousin going into the negative direction are identical. So there, in that case, the principal value will equal, if its limit exists, will actually equal the convergent actual improper integral. So for even functions, the principal value is a really nice tool. So now let's actually go do an example of how to use this principal value and use the residue theorem to compute these improper integrals. So what we're going to do now is now talk about functions of a rational form. So we're going to go back again to our f of x is equal to some p of x over q of x, where this is going to be some rational function. And now suppose that q of z now has n roots above the real axis. Okay, so what we're looking at here is the complex plane. Oops. Like that. And there are n roots above the real axis, and we can give those a little set name zk from k equals 1 all the way to n. Okay, and then finally also and then we also need to have p of zk is not equal to 0. Okay, we don't want any roots there. All right, now what we can do is, of course, look at this. We can look at this contour. I'm going to say this contour f of z now. So what we're going to do is transform this to an f of z. Will be p of z over q of z. Now I'm going to examine this contour integral where we have a contour that does this. It'll be positively oriented. I'm going to call this whole contour C, and then I'm going to call this CR. And it'll be of radius. Oops, it'll be of radius R. We can think of it as a giant semicircular contour with radius R, where CR will enclose all the roots that are above there. So there could also be roots below, but we won't worry about those. The whole point is that there are n roots above, and there are no roots on. I should say no roots, no real roots. All right, we can't have real roots, obviously, otherwise we'd have a singularity. Okay, so the question then is, this, of course, this contour integral is going to equal this 2 pi I times the sum k equals 1 to little n of the residue of f at z equals zk. All right, so that's nice. And if the contour integral CR of f of z dz goes to 0 as r goes to infinity, then, and this is the theorem, then the integral on the real axis will equal 2 pi I times the sum of the residues. Okay, and that's simply true that because we can call that you know, the interval negative r to r union with CR, that's equal to C, and if r gets bigger and bigger, then of course we have basically the real line there, union with CR, and that's going to be our C in the limit. And if the contour integral along this path goes to 0, then for every contour that's bigger and bigger and bigger, of course, we're always still just enclosing those roots there. Then, of course, the sum of all these residues times 2 pi I will have to be equal to the remaining integration part that does not consider that radial part. All right, so that, I mean, the theorem of it's pretty straightforward. Now what we're going to do is actually use this theorem. So again, it has to be true that the radial part of the integral, this contour integral, goes to 0 as r goes to infinity. And so we'll actually see how that does. So let's do an example to show you how this works. All right, so let's talk about this specific example. Let's say f of x is equal to x squared all over x to the 6th power plus 1. All right, so of course this is an even function. So that means the principal value integral equals the improper integral. Okay, so we don't have to worry about any convergence issues. Okay, so what's important though is that, you know, the goal then is to integrate f of x dx. Okay, so of course we don't have a nice antiderivative that we can find simply for this function. But what we can do is then look at it in terms of this as being our p of x, and that's our q of x. And we look for roots. So what we're going to do then is, of course, look for roots. So clearly, so we can find roots. So if you think of this as now as f of z is equal to p of z over q of z, and then we're going to look for those roots, q of z is equal to 0. That implies then that z to the 6th power is equal to -1. So we're just taking that there. Now I have to take the 6th root of this. So we find that z then is equal to the 6th root of -1. So that implies then that, so -1 I can write as e to the I pi over 2 plus 2 pi k as follows, where k then can be any any complex or any integer, and then of course the 6th root then there's going to be 6 of them, and it's going to be e to the I pi over 6 plus pi over 3 times k. Okay, so let's look at where those roots are. We have one at pi over 6, and then we have another one at I, otherwise known as pi over 2. And then there's another one at 5 pi over 3, right there. And then there's some more below as well. There's a bunch of them down there as well. Okay, and that makes all 6 of them. So there's one at negative pi over 6, and so on and so forth, just like before. All right, so of course we're just going to look at those top roots there. And then we're going to make a contour just like before, negative r all the way to r. We'll make r bigger than 1 so we can enclose our contours like follows, like that. So here on that contour integral, z is going to be equal to r. Okay, and clearly we're enclosing those contours there. All right, and so we can actually factor now f of z can be factored as, we have a z squared in the top, and the numerator, of course, we have that product of k equals 0 to 5 of z minus e to the I pi over 6 plus pi over 3k. All right, so that's a somewhat tricky function, but okay, so now we're really just looking for those 3 poles that are up here. And notice that this has all simple poles. And that means I can rewrite this function as a phi of z, which is analytic at each pole, divided by z minus zk. Okay, so those are our zk's there. I should write that down. These are our roots, our poles. Okay, to the 1st power. Okay, so the question then is, of course, we have to now use the residue theorem to compute all of those residues. All right, so we have it in this form. The problem is, of course, actually computing and evaluating this function at all of its poles, so that we can rewrite that now as going to be zk squared all over this product of we'll call it L not equal to k of z minus zl. So that's our analytic function divided by the one we want, z minus zk. Okay, and the problem with this is it's a bit unwieldy. So it turns out we're going to now use so let's now use our theorem, see if we can, we have a nice theorem from the previous video that we can use. So recall then, of course, that our function, f of z, while it's a bit unwieldy, we can rewrite it, so we had it in this form of phi of z over z minus zk. The k's we're looking for, of course, are 0, 1, and 2 to get those 3 roots. That one there, the one at I, and the one at 5 pi over 3. Okay, and so the contour integral over the whole thing is f of z dz is going to be equal to 2 pi I at the sum of the residues at zk k equals 0 to 3 of f, where the zk are, of course, e to the I pi over 6 plus pi over 3k. All right, so the problem with this is it's a little hard to find the values of phi, but we had this really nice result where the residue of f, if f is the form of p over q at zk, I can rewrite it as actually I can evaluate it to be simply p at zk all over q prime at zk. So this actually is a much more useful formula. So let's recall what this is again. F of z is equal to z squared over z to the 6th power plus 1. So of course if that's my p and that's my q, so that means that q prime is equal to, of course, 6z to the 5th power. So then that means that p over q prime is going to be equal to z squared all over 6z to the 5th power. I can rewrite that now as 1 over 6 times z to the 3rd power. All right, so now all I have to do is evaluate that at my 3 roots. Much easier to do. All right, so let's do that now. So that means this contour integral here, provided my r is big enough, it's bigger than 1, so it encloses those 3 roots there, is going to be equal to 2 pi I times. Now we have to evaluate this at the 3 points. So the first one is for k is equal to 0, and that's going to be 1, 6. And then what we have here is e to the I pi over 6 times 3, so that's going to be pi over 2, which is just I. So the answer is, of course, 1 over 6 times I. Very nice. And now what about k equals 1? That's going to be 1 over 6 times e to the I. Again, we have a pi over 2 there, just like before, but now we have a 3 plus 3 pi over 3k times with a 1 there. So we have a plus pi. So this means that is a negative I. So of course the answer then here is it's going to be a negative 1 over 6 I. And it turns out if you do the other one for k equals 2, you get the same thing as before. You get a 1 over 6 I, just like before. So our result then is going to be 1 over 6 I minus 1 over 6 I, and then a plus 1 over 6 I. And of course these two cancel, and we get out of this whole thing a simple pi over 3. All right, so now the integral around this whole contour for a fixed value of r is going to be this. All right, so now let's see if we can wrap this up here. So this contour integral was equal to pi over 3, and that was equal to the union of this negative r to r of f of x plus that contour integral CR of f of z dz. Of course, let's write that out again. So that is this part right there, and that's that principal value integral that we're going to take the limit of, and that's going to be our CR, this outer one, right? Okay, so that sorry, our roots are right there. Okay. So the next question is we need to now, so this whole thing is equal to pi over 3. The question is what happens when I take what happens to this part? Because eventually I want to just get the value of this as r goes to infinity, this principal value. And what would be nice is now we need to analyze I need to analyze this CR of z squared over z to the 6th power plus 1 dz. All right, so the way we do it, of course, is z is on the contour where the modulus is equal to r, and it's going from, well, 0 to pi. That's the integral. I could parameterize it and everything, but what I really want to do is just bound it. So what I'm going to do is look at this. So this thing, of course, is going... I'm going to bound this. So I'm going to bound this and see what happens. And of course, if I can, that'll be greater than or equal to the integral over CR of z, the modulus c squared, all over the modulus of the denominator. I can make this even bigger. I can bound this even further if I now do the triangle inequality. And that'll be equal to r squared. Now if I do the triangle inequality, we have to use that lower bound on the bottom, like this. Okay, and of course that's also r down there as well, r to the 6th. And so of course this no longer depends on z, this real valued integral. So of course I can move that out. That'll become an r squared all over r to the 6th minus 1. R is bigger than 1, so this I can take off these absolute values here. Okay? And then times the integral CR dz. Okay, that's an arc length integral, so that can be equal to r squared. This whole thing is r to the 6th minus 1 times, what's it going to be? Pi times r, because that's the arc length of this part up there. Okay? And now clearly, of course, now as r goes to infinity, what we have here essentially is we have a first power there, so we have a third power here, and we have a 6th power in the denominator. So clearly that goes to 0. And if this thing goes to 0, it means that this in modulus has to also go to 0. Therefore, we finally conclude, based on the theorem, that the principal value of f of x dx integral over the reals is equal to pi over 3, because that's what we had for our contour integral. Okay. All right, and because f is even, we can also say that it's no longer the principal value. It's the actual improper integral. Okay, so now we've been able to compute an improper integral that we've never been able to compute before if we just use real variables, but using complex variable techniques and the residue theorem, we actually had a solid result. So hopefully that gives you an idea of how you can use the residues to compute improper integrals. Thank you very much.